Hello, my name is Alfonso Fernandez, and in this tutorial you will find a practical exercise to delimit water bodies on a Sentinel-2 image using Snap. Once we have opened Snap, the first thing we have to do is to access the folder that contains the image. As you can see, it corresponds to a fragment of the original scene, whose date is 20 June 2023. Once this image is opened, if we unfold the whole folder structure, we could access the metadata where we would find all the information of the original scene. It's a level 2 product from which this image has been extracted. We could also access the masks folder, where we find a series of masks previously defined for this product. And we also access the folder that contains the 12 spectral bands that this image contains. For most of the water indices, bands 2 and 3, blue and green, band 8, NUR, and bands 11 and 12, SWR, will be used. If we visualize, for example, the NUR band, we can see how the pixels covered by water have clearly lower digital levels than those of land, vegetation, buildings, etc. The image, as you can see, has a high density of water bodies. It corresponds to an area in the northern part of the United States, near the Great Lakes. It is recommended that to facilitate the interpretation and understanding of this product, you visualize it in RGB combination. To do this, click on the right button of the mouse to open an RGB window. We are going to use the pre-allocation of bands corresponding to a false color infrared combination for the MSI sensor. As you can see, bands 8, 4 and 3 are used, and the result of this combination is the classic false color infrared, where we see that the water areas have clearly lower digital levels than the rest. To achieve the objective of delimiting the water bodies, we have to carry out a first step, which consists of the extraction of a series of water indices, images on which we are going to apply thresholding processes, and also, as an example, a simple process of unsupervised classification. But first of all, we have to generate or calculate the water indices. Within Snap, we can do it in two ways. We can use a set of indices that are already implemented, or we can calculate them using the Band Maths tool. The water indices that are implemented in Snap can be found in the menu. Optical Thematic Land Processing Water Radiometric Indices. You can see that there are 5 indices already implemented, and we are going to use the second and the fourth one as an example. EndWitWo is an index designed to identify and detect water bodies. It is an index that, when we calculate it, it incorporates the name of the index to the name of the resulting file. And in the Processing Parameters window, it uses bands 3 and 8. When we run the process, we can see which is the result that has been generated. It's a result in which, as you can see, the digital levels corresponding to the water pixels are noticeably higher than the rest of the scene. Let's calculate the second of the implemented indices, accessing the same menu as above. In this case, the NDPI is an index that is designed to identify small bodies of water, even those that have a surface area of less than 0.01 hectare, but it also allows us to characterize the contribution of the vegetation that is inside these ponds, inside these bodies of water. When we access the processing parameters, we need to do a resampling process first of all because we're using two bands with different resolutions, bands 3 and 12. This tool allows us to do this resampling in such a way that if we choose the higher resolution band 3, which has a pixel size of 10 is going to be used as the reference band. Now we can make the calculation and see how the result is not as clear as in the previous case, because it is reflecting the contribution of the possible vegetation that we have within these water bodies. We are now going to calculate a third water index. In this case, it's an index that is not implemented in Snap, it's the OISH index. This index is designed to improve the accuracy in the extraction of water bodies, but taking into consideration the effect of shadows, that is to say, it will minimize as much as possible the effect of shadows that we can find in the scene. To calculate it, we have to work with the previously resampled image, because 5 bands will appear in the calculation equation, each of them with different resolutions. So we have to resample the original image. To do this, in the raster menu, go to the option Geometric Resampling. In the Resampling Parameters tab, we are going to indicate that we want band 2 as reference band, the blue band, which is the one with the best resolution, 10 per pixel, and as upsampling method. We are going to use the bilinear method. We leave the rest of the parameters by default. And we can see how the resampled product with the 12 spectral bands has been generated almost automatically. From now on, we must always work on this image. Going to the menu Raster Band Maths, we are going to calculate the OISH index. For this, we're going to define the name of the band. And then we're going to edit the calculation expression. You can see it on the screen, and inside the expression you can see the blue band, band 2. The red band, band 3, the NER band, band 8, and the two SWR bands, bands 11 and 12. As we have previously resampled, we can see that there is no error in the expression. And we can proceed with the calculation. The result of this calculation is the image that you can see on the screen, in which the water bodies appear with digital levels clearly above the rest. This is a virtual band that we have to convert in order to integrate it into the structure of the file. To do this, right button on the name of the band, then Convert Band. We have already created 3 water indices. And now we are going to see how we can segment these indices to generate a binary water/non-water product. We are going to use 2 strategies, as I mentioned at the beginning. The first one will consist of defining a threshold, and we're going to apply this to the OISH index, the previously calculated index. We select the band corresponding to this index and go to the tool Raster Band Maths. We're going to create a new band that we're going to call Water Bodies. Then we edit the expression, and we have to enter a threshold. But what threshold are we going to use to determine what is water/not water? To define that threshold, we need to go back to the histogram of the index that we created. To do this, we go to Analysis Histogram. We click on the Refresh View button, and you can see below how this index has a clearly bimodal histogram. This means that we have a peak, an accumulation of the highest values, those corresponding to water at higher digital levels. And a second peak, much more important in those pixels corresponding to non-water. Between both peaks we find a transition zone in which we could approximate the threshold value to be used. In this case we could choose around the value 0.15. Once we have chosen this value, we proceed to perform the binarization. We go back to band maths and define the band to be created. We edit the expression and then we have to indicate which pixels are going to form part of or be identified as water areas. We have said that they are those that present a value of the OISH index greater than 0.15. And we generate the result. As you can see, it corresponds to a binary image with value 0 in land area and value 1 in pixels covered by water. As it is a virtual band, we convert it so that it is integrated into the image and we can see the result. The second way to get a binary image with water/non-water areas is to do a classification. In this case, we are going to perform an unsupervised classification on the same OISH index. To do this, we are going to access the menu. Raster classification, unsupervised classification, k-means cluster analysis. The resulting product will incorporate that information in its name. And as processing parameters, we're going to say that we only want 2 clusters. As input bands, we are going to indicate that we want the OISH band. Then we accept and execute the procedure. After a few seconds, the classification is finished and we can see the result, which is a new image containing a single band, as in the previous case, a binary image. Now we could compare the different results. By doing a shared window arrangement, we can compare the results with each other. Let's finish this video tutorial by remembering that the resulting products can be exported in generic TIFF format. To do this, inside the window with the right button, Export View as Image, we select the folder where we want to save the results and we indicate that. We want a GeoTIFF product of the whole image and with the maximum resolution. After a few moments, we have the resulting product in TIFF format, and we could incorporate it into our QGIS project. Later we could make the appropriate calculations and the analysis and processing that are necessary within an environment such as QGIS. So far this video tutorial, I hope you have found it interesting. Thank you very much for your attention.